Here's another person. I'm just going to admit people as they're arriving now, but our starting time is supposed to be 6:30. So welcome everybody. Apparently Chris is a highly regarded person in the telescope building business. So his talk on eyepieces should be very informative and very interesting. Apparently he was at some stage asked by the Americans to go and teach them how to build telescopes, so he must be pretty good. So yeah, you've all got his bio, and would like him to then start and get going.
All right, thank you. I'll start sharing.
Sorry, can I just mention for the people who aren't presenting, in other words, everybody else, please mute your mics. Let us know if you've got any problems with sound or picture.
All right, I think you should see my screen now. Yes?
So we can see it, yeah, it's good.
Okay, excellent. So, the first question about eyepieces is like, what's the point? Do you really need an eyepiece? What are they for? What do they do? And then you get lots of weird questions. How big should they be? What should I buy? And how many do I need, right? The gamut of eyepieces out there is huge. And so you can understand people's confusion about things. But firstly, do you need an eyepiece at all? Surprisingly, the answer is a qualified no, right? But using a telescope without an eyepiece is not a satisfactory experience visually. You'll have a very small field of view and you will strain to keep it in focus. Some telescopes are never used visually. The largest one I know of that is used for visual observing is this one in Texas. And presumably, an instrument of this size would have different requirements from what you might have at home. And that isn't necessarily true. And you will understand why when I've told you the rest. As we delve into this topic, then I might repeat some concepts a couple of times. And that's mostly because we need to internalize these things and remember them, right? So I hope you'll forgive me for a small degree of repetition. So the purpose of eyepieces are to match the eye to the telescope, right? And this is a very important issue. And so we will also talk about the eye as part of this, this presentation. Now, simple designs generally do not work very well on fast telescopes, in other words, telescopes with small f ratios, whereas slow telescopes are much more tolerant, right? Eyepieces are made for specific purposes. For example, integrated systems like binoculars, spotting scopes, and rifle scopes incorporate eyepieces. And they have a bit more design freedom because they don't have to fit standard telescope focuses and move from one instrument to another. However, we can use those and adapt them for our purposes as well, right? In the last century, eyepieces have evolved dramatically. And the enabling factors for this are the advent of computer-aided design and manufacturing systems, the industrial automation, wonderful ray tracing design software, material science, and notably a growing market of discerning amateurs that demands better. And that last has in turn been influenced by the advent of rather large short f ratio amateur telescopes, which have much more stringent demands on the eyepiece than those with long focal ratios. So the eyepiece is so important that it's really half of the telescope. And in fact, making a good high quality eyepiece can be more complex and more difficult than making the objective. So the eyepiece might be smaller, but it's just as important as the objective of your telescope in order to deliver a quality image. So the train that we have of the light passing through the system it's emitted from some large distant object, right? Passes through our atmosphere, which basically degrades things. Then the telescope, either a mirror or lens objective, gathers the light and focuses it to a small image. And that image, you can put your eye nearby and you can actually see it, right? But from there, it fans out again. And all the way through the system, there can be obstructions that generally sort of degrade the edge of the image by blocking the incoming light. That's called vignetting. And then many eyepieces will, in addition, have a field stop, which is a deliberate little sort of constriction on the aperture to give you a clean edge of your field of view. And these constrain the available field of view, right? Now, to accommodate our eyes, which struggle to focus so close on small objects, we normally use something like a magnifying glass or even a microscope. And in effect, that's what an eyepiece is. It's a device serving exactly the same purpose, taking a small image and it's producing a parallel beam of light coming out that the eye can relax for viewing at infinity, accommodate, and see. So as you increase the magnification, you're actually just looking at a smaller and smaller part of the image and making it look bigger, right? So obviously, there's only so much detail that is in the image. And so if you magnify it beyond a certain amount, you run out of detail. And this is analogous to getting too close to a television where the image breaks down and it gets pixelated, right? Here, it just gets noisy and blurry, but it's the same sort of thing. You've run out of resolution, right? But every step of the way affects your final image quality. So the eyepiece is a vital component for you to have a satisfactory experience. Eyepieces come in a bewildering array of designs optically. When we were younger, I say we, people of my age group, right, the Huygens and Rangstons were the norm, and a Kellner eyepiece was an upgrade, right? World War II brought the need for wide field eyepieces for gun sights, and that's how the Earthler became prominent. In life and death situations, as in wartime, right, no expense will be spared to give you an edge over the enemy. And so the military equipment demands more. And exposure to this, especially after the Second World War, when surplus equipment became available on the open market, right, people developed an appetite for wider fields of view than what the earlier lens designs had provided. Now, orthoscopics are much favored for planetary work, and even today, this is an excellent design, right? But a new type of eyepiece called the plethora came into being. And this had similar performance to an orthoscopic, but with a slightly wider field of view. In the 1960s, it was not believed that the plethora eyepiece would be commercially made cheap enough to become mainstream, right? By the 1990s, so-called super plossels, which are not really plossels, but they're sort of a development of that design with an additional element, right, came into being. And because two of the lens pairs are identical in this design, it's a symmetrical design. The light could go through either way and still work properly. But you had commonality of components. And that helped to reduce the cost of manufacture because less individual types of lenses had to be developed. You just make more of the same thing. So mass production techniques and utilizing these common elements enabled cost savings that allowed a bigger market to be addressed. But it didn't stop there, right? Already in the 1960s, the United States space race drove the need for superior quality, very wide field eyepieces for specialist purposes, And starting in that era, a famous guy by the name of Nagler developed a new kind of eyepiece specifically for the lunar excursion module trainer, where he had to simulate a view out of a porthole onto the lunar surface. And what they had was a little model of the lunar surface that was being viewed by like a small telescope. And he had to make it look as though they're looking through a porthole. And this was where the famous Nagler design originated. Now, such technology eventually became commercially available with Nagler making his own company called Teleview to supply his designs to amateurs. Since then, advances in material science has brought new exotic glass types to an affordable level, and computer-aided design and automated manufacturing processes have brought a whole slew of novel designs into the market. So I'll give a few here, and you can see as time goes by, it's become more and more exotic. So many of these use a long focus, wide field eyepiece as the basis of this, right? And then they add in front of that essentially a Barlow lens, which will amplify the image. It's also called a Smith lens, S-M-I-T-H. And this allowed for a shorter effective focal length. That means the whole system effectively has the same behavior as one single lens, but with a very short focal length, but of course with an added dimension of quality. More importantly, they allow wide eye relief. Now, all of these drawings I've done with the light coming in from the right and exiting the eyepiece on the left, so your eye would be on the left here. And so eye relief is the distance between the last element of the lens and where your eye's pupil should be for it to optimally match to the optics, right? So these designs are highly optimized, but naturally they're exotic, and being so are more complex to manufacture. You'll see many steep curves and many elements that all have to be of very high quality in order to match. And so they attract premium prices. Now, to look at some other characteristics of eyepieces in general, right? There are certain things that characterize that you can feel and see immediately. So the mechanical aspects, of course, are obvious. And one of the things that's most important here is the so-called barrel size. Now, this is where the eyepiece has to plug into your telescope, and if it won't fit, then obviously you can't use it. So at a relatively early stage in the 1900s, the need for mechanical standardization to ensure interchangeability of eyepieces was recognized. And although it started in Germany, this 0.965-inch 25.4 millimeter standard originated, nobody seems to know why it was chosen. And it was later popularized by the Japanese in particular. In its heyday, companies like Zeiss, Nikon, Unitron, and Neon Seiko made really exquisite examples of eyepieces in this size. Size has simply since been abandoned due to the adoption of larger focuses, and is only used now for entry-level instruments due to cost constraints. The recent versions in the last 25 years or so tend to be of quite poor quality, and buying these is false economy. But if you can find one of the early ones, it's probably quite decent. Now, around about the same time as the 0.965-inch barrels came into being, the French perversely chose the Paris inch, which is 27.07 millimeters or 1.06 inches. Again, nobody knows how the hell that arrived, and thankfully that is long since defunct. The British, of course, had to be different. And they chose what's called RAS thread, right, which was essentially a standard plumbing thread of 1¼ inch diameter and 16 teeth per inch thread. So The advantage of this is that it's secure, it screws into the instrument and won't fall out, but it makes it difficult to change the eyepiece quickly, and the process of unscrewing it might cause you to lose your target object. Then the Americans developed a now ubiquitous 1 1/4 inch standard, which you'll see here. And this barrel is quite significantly larger than a 0.965. And now today, the 2-inch eyepiece is the standard. An emerging standard is a 3-inch barrel. And that's an expensive proposition suitable for very large telescopes. Now, one has to ask why this progression from these small sizes to ever larger sizes. Well, the larger the barrel size, the larger the field stop, which is, as I mentioned earlier, a constriction in the train. And because that's larger, then the available field of view also is larger. So small barrels are a limiting factor. And for 0.965 inch, the maximum apparent field of view that you can get, no matter how wonderful your design is basically 40 degrees, which is not so bad, but you'll only get that in the very, very low power eyepieces. Now, another thing to notice is on the older eyepieces, the tiny eye lenses, even on the 1 1/4 inch RAS thread, really tiny eye lenses. Now, at the time, manufacturing costs were high for this type of thing. And so, glass was expensive, and you can understand that played a part in it. But, we demand better these days. So larger barrels allow larger optics. And the larger the barrel size, the larger the available field of view. Now, having more glass is good. It accommodates exotic designs to produce modern benefits, such as long eye relief, which normally scales with the focal length, but with recent designs, that restriction has more or less been done away with, which is wonderful for the comfort of using your eyepiece, right? However, the larger sizes are also limited by, colliding with your nose, right? We all have this protrusion on our faces close to our eyes. So you'll see this so-called volcano top arrangement on many eyepieces these days, right? From different manufacturers. And that's partly so that your nose can get by and you can actually center your eye on the eye lens, right? It's generally possible to adapt smaller barrels to larger focuses. Simple adapter mechanically will do that for you. And the best is if it's got this brass compression ring so that the screw isn't actually graunching on your eyepiece barrel. Going the other way is not so easy because you've got the mechanical constriction, right? Some of the modern eyepieces allow you to move between 1 1/4 inch and 2-inch focuses deliberately because they have a dedicated adapter that screws onto it. And others like this Barlow over here, there's a teleview at the top, this Barlow at the bottom here, you'll see that it's got a skirt, which is 2-inch, and then it's got a nose piece, which is 1 1/4 inch. Another teleview eyepiece here has got basically 2 skirts, right? One 2-inch, one 1 1/4 inch. So the backwards compatibility is there to an extent, but others are just 2-inch, and there's no getting away from that. So those that are sort of dual barrel size tend to be the shorter focal lengths where you're not going to have such a wide possible field of view as you would with the low power of something like a 30mm eyepiece. Right? Mechanically, there are some embellishments that we can consider that will separate the lesser quality with those of a higher value. And most of these things are sort of obvious if you just look at the telescopes, such as rubber eye cups. We've got used to this now. That didn't used to be the norm even 30 years ago. And so they can fold down, same eyepiece with the eye cup folded up and folded down. They can fold down for those of us who wear glasses and need the vision correction to be able to get a satisfactory quality of view. Or they can pop up so as to help center your eye and block out light from the surroundings. Rubber grips, of course, are quite sort of obvious, and anybody who has dropped their expensive eyepiece on a tiled or concrete floor will know the anguish. So especially when your fingers are cold, it's very nice to be able to grip securely without difficulty. Some, like this William Optics here, are waterproof, gas tight, and purged with an inert gas. So even if you dropped it in a bucket of water, it would survive the experience. You wouldn't enjoy it, but the eyepiece will be all right. And most importantly, because it's been purged with some inert dry gas, as the temperature drops, you won't get internal fogging within the elements within the eyepiece. A few have got hidden features like this barred Hyperion, where you can remove the rubber eye cup from it, and you'll see that it's got specific mechanical parts there. And notably on the side here, these weird little threads. And this is part of a system that makes it modular, so you can plug in things for like eyepiece projection and so on that otherwise are mechanically quite difficult to accomplish, right? As for the engagement with the focuser, some of them have got a recessed area, as you can see here and here. That means that if it's not firmly screwed in, these will at least engage on the clamping screw and help to prevent the eyepiece from slipping out, right? Others, like this adapter here, you see it's got a small taper on it. And generally the taper is to be preferred because these grooves they're safety grooves really, but they can bind to the compression ring of your focuser and make it more difficult to get out easily. So if you're looking at the mechanics and that's going to be your last criterion for deciding whether to purchase, that is really something to look at. Next up, of course, quite obviously is the mass. Some of these things, I mean, this 30mm, we talk of it as being a grenade, but grenades are nothing. I mean, look at the relative sizes and the relative weights. I mean, this thing weighs over 1 kilogram, and it's like half as big again in diameter as an actual grenade, right? So the mass scales up rapidly with the barrel size. So you have to check before you go and buy a monster like this. Can you actually balance your telescope? You might have to make special provision for it. It's not just can it fit in your focuser, but will you be able to use a telescope with this thing installed? This is particularly true of minimalist Dobsonians. And for those, you might have to add a small movable counterweight. Another possibility is you can choose between different ranges from different manufacturers for the focal lengths that you require in order to keep the difference in weight between one eyepiece and the next in your set similar. So here's just a little summary over the years. You see there's a huge difference between 30 to 45 grams versus 1.5 kilograms, right? And I dread to think what a 3-inch eyepiece will weigh. So with the mechanical aspects behind us, we can look at the optical characteristics. And the most prominent, of course, is the focal length. If you change the focal length, you're going to be changing the magnification, which is something that people seem to cling to as being an important issue. And here you will find that if you buy a set of eyepieces from a specified range, they might all be very, very similar mechanically, and they might even have similar eye relief, right? So the focal length is the primary distinguishing factor. Maybe you will find the odd eyepiece that's below 3.5 millimeters, but normally it's about 4 to 5 millimeters as the shortest focal length. And on the longer end, it'll go up to 40 or 36 millimeters. You do get longer. I've got a 75 millimeter in my collection, but it's not something you're going to use very often. And you'll see a bit later why that is the case, right? Zoom eyepieces provide continuous or click stop, right, with set focal length, series of focal lengths in a single eyepiece. Now, is this good or bad? Well, it depends. It's quite useful for travel if you only take one eyepiece instead of maybe 5, right? Less to lose, less to carry, right? And it's quite nice for telescopes that are shared, like so-called library telescopes or your club telescope. Less items to worry about looking after. And especially it's good for those of us who might have bino viewers, so that we can use 2 eyes, because it's cheaper to buy one pair of zooms than it is to buy a pair of each focal length that might be of interest. But of course, the quality can be highly variable. And good ones like this Barlow are excellent, but most common ones are not, right? And these older ones like this had a deservedly bad reputation. I mean, the thing's basically junk by our standards of today. Might have been a marvel of engineering to make it work at all. And the fact that they've persevered to produce decent ones today is good. But I would say it's generally better to get a few decent fixed focal length eyepieces than to rely on zooms, unless you have a specific requirement, such as having shared telescope or bino viewer requirement. So still on the subject of focal length, right? What does this do? Well, eyepieces of different focal lengths will produce different magnifications on a given telescope. And here we illustrate using eyepieces that have the same general characteristics, but they've got different focal lengths. So here the magnification numbers are just illustrative, right? But you can see that the telescope's only capable of delivering a certain amount of detail. So if you pile on the magnification too much, the image will break down, right? On the low end, the exit pupil becomes too large for your eyes pupil to accept. And then the shadow of the secondary will create an annoying hole in the image. You see this as a black spot in the middle. And particularly when you're looking at a bright extended object like the moon, right? And also the finer detail is not large enough for you to be able to appreciate. On the higher end, eventually you run out of resolution where the image just breaks down. It's very much more limited by atmospheric effects, and it's much more sensitive to vibration. And both of these extremes, as we'll see just now, are affected by defects in your eye. And we will discuss the interaction with the eye later. So these images, same apparent field of view. So we assume a specific design of the eyepiece, right? But they're different magnifications. And you see, all we're doing is we're looking at a smaller and smaller portion of the image, and we just use extending its apparent field of view for us. Now, extremes. What we see here is a 60-inch Rockefeller telescope at the Boyden Observatory in Maselfurt outside Bloemfontein. 60-inch primary, it's 1.5 meters in diameter, right? It started off as a Newtonian telescope. You can see this guy in this little cage here that was like quite like a lift, if you will, that will get into the eyepiece up there, right? But the quality of it was not particularly good, and it got converted to an F16 Cassegrain in 1968. And this instrument now has a 23.82 meter focal length. It's the third largest telescope in South Africa after SALT and the 74-inch at Sutherland, and it's the fourth largest in Africa. There's another 74-inch in Cairo. I managed to use this long ago, before such things as public viewing on the instrument were possible, because it was still being used for research. And in order to use it visually, because normally it had things like spectrographs and micrometers and so on it, I made a 100mm focal length wide field eyepiece for this. It yielded a medium power view at 237 times magnification, with a 2.4mm diameter exit pupil, which was quite all right for visual observing. Now with that, Omega Centauri covered several eyepiece fields, and it took me 20 minutes just to get Jupiter into the field of view. That's what the true field of view was, so narrow. And if you wanted to use this with low power, you would need about a 250mm focal length eyepiece. I did something similar for the 26.5-inch refractor in Johannesburg, and mysteriously both eyepieces have vanished. On the other extreme, eyepieces under 2mm focal length do exist, but they tend to be very uncomfortable. So on to the apparent field of view. What we've got here is an image at a given magnification, and the apparent field of view is larger and larger as you go to these outwards on these circles. So although I've got here some examples of eyepieces that happen to have different focal lengths, the point behind it is the apparent field of view that you can achieve, right? You can see it goes from 35 here, 50 degrees all the way up to 110 degrees in these examples. So same focal length, same magnification, but different apparent field of view means we can see a larger part of the image produced by the telescope. Now, eyepieces with a different apparent field of view will show smaller or larger portions of the sky, of the image, and thus of the sky at the same magnification. And as the apparent field of view increases, the design is forced to use large and complex lens systems, and this soon gets very heavy and very expensive. 50-degree eyepieces used to be a premium, right? And this high-performing 8-element example is something that I built from junk. So it cost me maybe 5 rands worth of materials. Right? It would have been a fortune not too long ago. Now, wider fields are comfortable and people like it. As you start getting to the extremes, you actually need to roll your eyes around to see the peripheral detail, as we'll soon discuss. But it's generally an unnecessary expense, right? However, for short focal length eyepieces, which produce high magnification, does help you to find the object, to keep the object in the field of view, and especially so if the tracking of your telescope is poor. And it is this that has really driven the trend towards larger apparent fields of view, because we have some quite large amateur instruments that are Dobsonians, alt-azimuth mount that is untracked. And so having the wide field of view makes it so much easier to find the object and keep it in the field of view. Next up is eye relief. As I said, eye relief is the distance between the eye lens of your telescope and your pupil ultimately, right? And for you to see the full possible apparent field of view, you need to have your pupil exactly at the exit pupil point, right? So we want this to be larger, right, if possible, because it's more comfortable. But then we might need eye cups to help shield extraneous ambient light and to keep the eye centered on the exit pupil. Generally, the eye relief is shorter with a short focal length eyepiece and larger with a large focal length eyepiece, so it scales with the focal length of the eyepiece. Clever designs can help improve that, but that of course comes at a cost. Long eye relief and eye cups are strongly recommended for public viewing. And I'm not joking when I say, especially to protect your precious instrument from a scar You'd be amazed how much gunge you'll get on your eyepiece from people wearing mascara and they're batting their eyes at the instrument and it scrapes on there and just gunks it up. So we saw earlier how eyepieces with short eye relief and tiny eye lenses used to be the norm. And in fact, short eye relief can present a significant danger to the observer. Now, it's not least by bumping or scraping the surface of the eye, right? In the case of we've got here is a rifle scope, right? The recoil of the firearm can drive the eyepiece straight into your eye. And many people who have been using their rifles improperly have suffered from this. But there are even more dangers out there that are not intuitively obvious. And for this, I got a little anecdote. I read of an elderly observer alone atop a remote mountain, observing in cold weather. He turned away from the eyepiece in order to make some notes and found that his vision was suddenly blurry. So it turned out that his contact lens had frozen to the eye lens of the eyepiece. Now, imagine if that had been his cornea stuck to the telescope instead. And even if he'd had that realization that his eye was now frozen to the telescope, if it had a RAS thread, he would be screwed in the literal sense of the word, because he wouldn't be able to undo the eyepiece. That's something to think about. Now, eyepieces beyond the actual lens design, which is giving it its primary characteristics, have other aspects by which you can judge them. So good quality eyepieces will use exotic glass types to control aberrations, and they will take quite extreme measures to control glare. So good coatings are one attribute that premium eyepieces have in common. Every single glass surface has the potential for reflection, and the more surfaces there are, then the exponentially greater number of potential reflections. Now, internal reflections occur when there's an abrupt change in refractive index, for example, at the air glass surfaces. That's why you can see windows, right? It's not because the glass isn't transparent, it's because the surface reflects a degree, and we can see that reflection, know where the boundary is. Single internal reflections can scatter light across the field. So this is if the light's coming from the telescope and it's like a single surface, then the light can scatter from there. Even numbered reflections, right, can lead to ghosts. So what happens is the light comes in, it's reflected off a surface, then back towards the telescope, and then it hits another surface, which is the second one, right? And from that, it can come back to the eye, right? And that's when you see ghosts like this, right? The number of ghosts goes up exponentially with the number of surfaces, right? It's really quite serious. So exotic lenses with many, many elements in them are more prone to this. And therefore, the necessity for having good quality coatings is very high. But not all of the ghosts are in focus, and those that are not also scatter light across the field, and the scattered light reduces contrast. Modern coatings are very good, and coatings only really came about around about the Second World War. And even the best can't entirely eliminate perceptible ghosts. Right? What we see here is an extreme case. I used very serious lighting to take this photograph, and that's why you can see these. This Barlow Hyperion on the left is what's called a phantom coating. And, excuse me, it's so good that under normal conditions, it's hard to tell where the surface of the lens is, right? So, but with a strong light glaring on it, we can see the reflections inside here. So all of these measures help to improve the contrast in the observed image. So exotic glass types, blackened edges to the elements so that you don't have internal sort of non-specular reflections of the edges of the glass, and the superior coatings. All of them, the purpose is to improve your image contrast. I'm now going to divert a little bit to accessories that are allied to eyepieces. So, these typically fit between the telescope and the eyepiece or camera. And some screw in and some are slip fit, just like the eyepieces. And you can argue that they're part of the telescope or that they're an accessory for the eyepiece. It's a bit of a gray area, but the point is to improve the performance and utility of the system. And all of them can potentially improve some aspects, but of course, they also can introduce their own issues, which may degrade the image in some other way. And I'm going to look at these in turn, because I think while they're not strictly according to the scope of the talk being eyepieces, they are so closely associated with the eyepiece that the interaction between these and eyepieces is something to pay attention to. So firstly, we have Barlow lenses, right? And the purpose of the Barlow lens is to achieve a longer instrument effective focal length. So we've got here this green ray coming in. This is the original focus from the telescope. We put the Barlow lens in, and what it does is it stretch it out. So you'll see that this angle changes with respect to the original, and that angle and the new focal point make the eyepiece think that the telescope has a longer focal length than it actually does. So you could argue that it is like, say you've got a 2 times Barlow, you could argue that it's halving the effective focal length of your eyepiece as far as magnification is concerned. But really, its purpose is to increase the telescope's effective focal length. Because the eyepiece sees a larger effective focal length, right, it's actually much less harsh, or less demanding task for the eyepiece to deal with. This can help to enlarge the image to better fit a sensor or give a magnification boost for visual work. And Barlows are generally available from about 1.5 times through to 3 and up to about 5 times magnification. The early Barlows were poor quality. They produced degraded images and they deserved their bad reputation, yet they still had enough utility that they persisted, right? Modern apochromatic Barlows use exotic ED, that's extra low dispersion glass. They're very good and they're actually relatively inexpensive. And they can help simple long focus eyepieces to provide a better quality, higher power image, whilst retaining comfortable eye relief, and particularly to better deal with the broad cone of light coming in from fast telescopes. Now we have Dobsonians that are like f4.5, right? This is pretty vicious for eyepieces to have to deal with. That wide angle of incoming light requires quite exotic designs. So by using a decent Barlow, you can improve the behavior of your old eyepieces on a modern fast instrument. Stacking Barlows in series to make a sort of super Barlow with extra high magnification factor does work, but the image quality usually suffers. Barlows are not really recommended for modern complex eyepieces because, as I explained earlier, they typically have what amounts to a built-in Barlow lens. And so that really means that you are stacking Barlows. Nonetheless, it's an economical way to effectively extend the range of eyepiece focal lengths in your set if you choose wisely the parameters to avoid duplication. And it also means that maybe if you go out into the field, you don't have to carry so much stuff. Maybe 2 eyepieces on a Barlow instead of 4 eyepieces. When choosing a Barlow, you have to consider the amplification factor and how it relates to the focal lengths of the eyepieces that you have. So we can look at this amplification factor as increasing the focal length of the primary instrument or decreasing the focal length of your eyepiece in terms of what it does to the magnification. So we'll look here, these bands of color are showing you as you use the same eyepiece, right, with a Barlow, then different focal lengths will be duplicated. So you could have in your range like a 10 and a 20 and a 40 millimeter eyepiece. And if you use a 2 times Barlow with your 40 millimeter, then your 40 millimeter behaves like a 20. And if you use it with your 20, it behaves like a 10. So what you've got is 3 eyepieces and a Barlow, but you're actually only getting 5 effective focal lengths out of this lot. So it's just something to pay attention to. The opposite of a Barlow lens is a telecompressor, which is a focal reducer. So here we have the green light of the original beam coming from the telescope, and suddenly this is reduced, and so it gives a wider incoming angle, right? And the new focus is closer to the telescope and so farther away. So telecompressors shorten the telescope's effective focal length, right? And so it's synthesizing a lower focal ratio, F ratio, of your primary instrument. Normally these screw into place, and this is partly to critically position them within the optical train for optimum performance. And they generally apply to photography, where they can be used to reduce the magnification for visual use, but it's better to use a proper low power eyepiece if you have that option. I'll give you a little anecdote a bit later about super low power involving the use of telecompressors. Now, there's something that really does belong as a component of the telescope as opposed to the eyepiece, and that's field flatteners and coma correctors. So all telescopes, even rather expensive ones, tend to suffer from field curvature, right? We expect a nice flat image plane, right? But in reality, it tends to be curved. It can be curved away from the telescope or in the opposite direction towards the eyepiece, right? And this is a natural consequence of simple optical designs. But for ideal coupling between the telescope and the eyepiece or the image sensor, the focus should lie on a plane. So the eyepieces are designed to look at a plane image. And so if the image plane is not flat, then you're going to get degradation towards the edges of the field of view. The shorter the focal length of the instrument, the shorter the radius of curvature of this image surface. And high-end telescopes, especially for astrographs, would correct this in the optical design. But short focus instruments can particularly benefit from a field flattener. Dedicated systems can compensate with special eyepiece design, but then, of course, that eyepiece is not interchangeable anymore because it's dedicated to the purpose. Another image aberration is coma. And coma can occur in all instruments, but it's particularly significant for fast, that's short F ratio Newtonians. And the reason is a parabola can only focus stars to a point at the very center of the field. And then as you move away to the edges, the pinpoints fan out like this. That's a simulated image, greatly enlarged. If you saw this, you would be very upset about it. But the image gets soft around the edges. The stars are not crisp little pinpoints anymore. So the degree of coma depends on the focal ratio of the telescope. With faster, that's shorter focal ratio telescopes showing more coma. And one way to characterize the level of coma is what's known as the coma-free diameter. So at your focal plane, the diameter from the center, right, around the center, the size of the region in which the coma is not objectionable. It doesn't materially affect the field of view. This tends to be quite generous. You can see with long F ratio telescopes, but it becomes quite restricted with short focal length telescopes. And with the move towards short focal length Newtonians in particular, I would highly recommend that you look at a coma corrector. Now, a weird thing, incidentally, is that coma is independent of magnification. When you magnify, you're looking at a smaller central portion of the image and enlarging it, right? So the smaller amount of coma that is at the center is also enlarged. And the distribution of coma across the field of view through your eyepiece thus looks the same at different magnifications, even though, in fact, the telescope is delivering different amounts of coma from between the center and the edges of your field of view, right? So often field flattening and coma correction are combined, and that's especially helpful for short focus Newtonian telescopes performed properly, right? I must caution that sometimes astigmatism is confused with coma, and often the astigmatism is in your eye as opposed to in the telescope itself. Anyway, I would more characterize such things as being part of the telescope rather than the eyepiece, but it's something your eyepiece has to deal with, and that's why I'm mentioning it here. Next up, we have filters, right? They're actually a topic on their own, and they're most important for specialist applications such as astrophotography and solar observation. And because the topic of this is eyepieces, I'm going to concentrate on the visual requirements here. So filters may be designed to attach directly to the telescope, such as here, or to screw onto the eyepiece, such as these ones, or possibly to fit in a filter tray or filter wheel or drawer or adapter between the telescope and the eyepiece. And I would recommend, if you're going to be using filters a lot, that you should look at a filter tray, because it allows you to quickly swap out filters without disturbing the rest of the optical system. Unfortunately, that does have a thickness to it, and therefore, by adding the space between the telescope and the eyepiece, in some instruments, you may not be able to achieve focus. That's a bigger problem for Newtonians, and it's much easier for things like Schmidt-Cassegrains, where the mirror slides and pushes the focus in and out of the instrument. Filters were rather important on old refractor telescopes that suffered low definition and chromatic aberration. And it's less so with modern instruments, especially upper chromats. But colored filters can still help with certain planetary details, because if you look at Mars, for example, you can bring out higher contrast by choosing some filters carefully. Then we have variable polarizing filters, such as this. And the purpose of this is you can adjust them with respect to one another angularly. And that polarization will then block more or less light. And so this is useful to deal with the glare of the moon, and that's what they're usually sold for. But they do tend to be fiddly to operate. So these are designed to screw onto your eyepiece. And now what you've got to do is pull the eyepiece out to turn the one with respect to the other and put it back and see if it's in the right position. Now you get used to this. And once it's there, then you can observe for a reasonable period. But you know what? You could just increase the magnification, and the image brightness will therefore drop, because the same amount of light is being spread over a larger angular area, right? Generally, I would not suggest you buy cheap filters. They're really not worth the price. And I'm not really keen on basic screw-on colored filters, because they're so fiddly. But if you want, fine. But I suggest you just get what you actually need. Now, beyond those basic things, we get special filters. And if you have an achromat filter, I would strongly suggest you get one of these, right? One of these, or the equivalent from a different manufacturer. These are known as fringe killers. So if you look, this top spectrum here is what's getting through the system, whereas the bottom spectrum is what's arriving at the system. And this is more or less at the limits of the reasonable range of spectral wavelengths that the eye can perceive and focus nicely. And what it does is, by cutting off sharply, you don't get the sort of purple haze, you know, that weird sort of fringe coloration that you see, particularly on bright objects such as the edge of the moon or bright planet with a refractor. Of course, if you do this, you're not changing your instrument into an apochromat, but you're getting similar quality image as a result. Right? And I can talk a bit more about filters afterwards if you like, and I'm going to move on to the next part of the eyepiece topic. So you see kits on offer, and what should you do, right? Well, sometimes you can get a bargain by buying a set of eyepieces in a family. And these barred Hyperions are excellent quality, both optically and mechanically. And they're part of a system that allows the eyepieces to be used in unusual ways. I mentioned earlier that they've got these hidden features to them, and the coatings are exceptional. So if you can get a set of, if not these, something else that's a high quality eyepiece set, right, by all means. But the question is, do you actually need the whole range, right? I mean, economically, the more exotic the eyepiece, the higher the cost, and you've got to look at your price performance ratio there. So probably you don't need the whole set, but we can look further at that in a moment. As for the lesser quality kits, well, you know, Celestron's fine, right? And maybe this kit is better than the one to the left with the no-name brand, right? And you get a case, which is nice, right? But do these eyepieces fit your actual needs? Well, they're a good fit for your telescope's focal ratio, right? And what will you do to house all your eyepieces as your collection grows, right? Generally, these kits are a marketing ploy, right? They entice you to think that you're getting a bargain on the basis of counting all the parts that you get, right? And I suggest that you do your research, you try before you buy, and determine what your actual requirements are. Just get what you need. So quality counts. A few high quality eyepieces are better than a whole slew of lesser quality eyepieces. And if you've chosen carefully for the objects that you like to look at, then you will appreciate doing this. All right, now we're coming to what is perhaps the most important part of this talk, and I also hope that you'll find it the most interesting. To fully understand your eyepieces and to make appropriate choices, we need to understand how the eye itself works. In this sketch, we're looking down on your right eye from above. The left eye is just a mirror image of this. So the overall structure is essentially spherical. And we've got muscles on the outside here that can roll the eyeball up and down and left and right, okay? And then there are muscles on the inside that can pull on the iris in order to control the pupil, which is the hole in the middle of your iris, and to pull on the edges of the lens, which is a bit squishy. And so you can then change the focal length of this lens in order to focus the image. Right. The light enters through the cornea, and this air to tissue surface, right, represents a big change in refractive index. And so the cornea is where the majority of the deviation of the light in order to form an image occurs, right? And so most of the focusing is done with your cornea. And then by adjusting the shape of the lens, you can adjust the focal length of the overall system and thereby also accommodate different distances of objects to bring them into focus. And in fact, that is called accommodation within the medical industry. Now, the quality of the image produced by the outer portion of the lens is not as good as that through the center of the lens. This is quite important to bear in mind, as you will realize in a little while. The eye is inflated. It's got in the front here aqueous, which means watery, humor, which is like a sort of jelly kind of substance. And on the inside, vitreous, which means jelly, right? Humor. Those are just the medical terms for it. And it is the pressure of this that inflates the eyeball and keeps it spherical. Unfortunately, the blood vessels and nerves sit on the inner surface of the retina, which is the photo-detecting part of the system. And because these things are static, right, you know, the blood vessels don't actually change position, the brain can sort of ignore that as being sort of normally there. And because your eyes are symmetrical, right, the differences between the one and the other get integrated by the brain, and it just fills in from the one eye what it can't see in the other eye, and you don't notice this, right? Under extreme conditions, such as when you're using a telescope for high magnification, where you've got a thin pencil of light coming through, then you start to see these structures on the inside of your eye. And telescopes present a sort of unnatural challenge to human vision. Other creatures actually have quite different eye structures. Ours is common for mammals, but even within mammals, there are differences. So cats, for example, have a reflective layer behind the retina. So the light that passes through the retina gets reflected back. So the retina has twice the opportunity to actually collect those photons than what we have, right? And that's why cats can see so well in the dark. Crabs have a reflective rear surface, not a retina here. And then in the middle of the lens, they've got their photoreceptors. So their eye system is actually very similar to a Schmidt camera. And insects have something very different. They've got compound eyes with waveguides instead of lenses, and each waveguide feeds an individual sensor. So they don't have a single lens that pipes the light to multiple sensors. They have one little, like, not lens, but waveguide per sensor. So just to summarize that bit is that the beam of light coming in is restricted by your pupil, but the pupil can change size, right? Iris controls the pupil diameter, and the maximum diameter of this is very much age related, right? So the minimum pupil dilation depends on age, genetics, health, and the lighting conditions. The maximum dilation of 7.5 millimeters is a generalization, and that really comes from the fact that it's a sort of reasonable average of people of military age, right? You know, youth going into the military, that's about what they can manage. But for some individuals, it can actually be as much as 9 millimeter, all right? You know, small children even. But it can be much less in others, especially as you get older. It tends towards a smaller maximum pupil, right? Now, just as with a camera lens, if you stop down the lens, then you increase the depth of field, which within limits improves the image quality under normal terrestrial conditions. With us using telescopes, there's some peculiar circumstances that the eye wasn't specifically designed for. And that means that we can see weird things that I'll mention a bit later. Now, we've discussed how the image is formed, but we need to know a little bit more about the retina and the blind spot, and where is vision most acute, and so on and so forth. So this is where things get complicated. Defects in the eye's lens or the cornea can be medically corrected, glasses or surgery, right? But not the retina. If you damage the retina through disease or excessively bright light, ultraviolet exposure, or some mechanical injury, right, then it's just not going to get better. the retina is the surface, the sensor on which the image must be focused. And through a complex set of photochemical and electrical responses, photons arriving at the retina are translated into an electrical pattern, which get channeled to the brain by the nervous system. And in fact, because the nerves come directly from the brain, and in fact, the eye is held in a socket that's an aperture in your skull, and the nerves are sort of indistinguishable. They just they might have specific differences, but as nerves go, they really can be considered to be part of your brain directly. That's how tightly coupled the retina is to the brain for human vision. Now, there are two kinds of photosensitive cells. There's actually a third that I'll just briefly mention later, but for vision, there are two kinds, and they are rods and cones, and they're named after the apparent structure. If you look at the retina from the surface, you see little dots, and those little dots have got shapes, and some look like rods and others look like cones, right? The cones are optimized for high definition color vision. We've got three distinct types, and they're represented here as red, green, and blue, right? And they specialize in responding to red, green, and blue portions of the spectrum. And overall, there are about 7 million cones and about 120 million rods in the retina of each eye. So ultra high density monitors have got nothing compared to the eye in terms of density of sensors here. So the cones are highly concentrated in an area called the fovea, and fovea means pit for its physical structure. The fovea is actually only about 0.3 millimeters in diameter, where your vision is most acute. And it's more sparse, and the cones are more sparsely arranged as you move away from that area, right, into the surrounding, still very high definition area called the macula. So cones do not work under low light conditions, but bright colored objects like the planets can trigger them and afford high resolution views. Right. The blue sensitive rods are arranged mostly towards the edge of the fovea. Okay, and they only, the blue sensitive cones, right? Not rods, the blue sensitive cones are arranged around the edges of the fovea. And you can see this distribution in the center. There are very few blue sensitive cones, and then they get more, progressively more as it goes away from the center of the fovea. And the blue sensitive cones only amount to about 2% overall of the number of cones. The rods, on the other hand, are optimized for low light monochrome vision. And there are no rods in the fovea. Their peak density is about 18 degrees away from the fovea. They respond very well to low light conditions, and they're slightly more blue sensitive than the average cone response. The other function is detection of peripheral movement. Now, for viewing faint objects where the rods are not that sensitive, the cones are not that sensitive, astronomers use averted vision, and that places the objects of interest on the high sensitivity area surrounding, in the macula, surrounding the fovea. And that's slightly off center. If you look at this line here, you can see that this is off center, but we're talking about off center with respect to the fovea. Small movements of the eye can then make objects on the threshold of visibility blink in and out, because your eye dithers a little bit, and the light will fall on the acutely sensitive area or not as you move your eye slightly. So on the threshold of sensitivity, things can blink in and out of view. And we learned to do what's called averted visions to deal with this. It's not so easy. Now, our perception of faint light and small detail is highly dependent on the number of ganglia involved. Now, ganglia are nerve complexes where the rods and cones are connected to. And so the rods and cones detect the light, and then they feed electrical impulses to the ganglia. And the result of this is that there's a 40 to 50 degree field of view where, actually, I must just backtrack a second. The rods and cones are connected to ganglion cells, right? And the purpose of the ganglia is to do pre-processing. So in the fovea, there's typically one ganglion per cone in the fovea. And on the periphery, there are about 100 rods per ganglion. And that's where movement is detected. Remember, danger comes from the periphery, so it's quite reasonable that the body is designed that way. Okay, now, whether we perceive anything is highly dependent on the number of ganglia that are involved. So the brain has like a voting system here. If one ganglion says something and the ones around it say nothing, then the sort of majority rule is there. And this is probably something to do with dealing with noise, right? You know, if you get one little blip somewhere that's spurious, maybe a cosmic ray is connected, you know, then it gets voted out, and the eye brain system will ignore it. Right. So the perception of faint light and small detail is highly dependent on the number of ganglia involved. And we've talked about the distribution of this, and the result is that a 40 to 50 degree field of view is generally quite sufficient to provide a satisfactorily detailed view. And to see a wider field of view, then we must roll our eyes around and let the brain synthesize a wide field view from a bunch of mental snapshots, right? Because remember, the outer area is not very acute in its definition. It's only in the macular area, in particular at the fovea, that you have high definition, right? Now, photoreceptors are extremely sensitive. And in addition, we have a secret weapon in the form of a chemical turbocharger. There's a substance, a chemical called rhodopsin, which is also known as visual purple, which is secreted by the eye. And it floods the retina, and it greatly enhances the photosensitivity. However, rhodopsin itself is light sensitive. So it gets bleached, a chemical term for it, into ineffectiveness when it's exposed to too much light. And that then dampens our visual sensitivity. And this works together with the iris so as not to overload the system. So when the light is bright, the iris stops down to reduce the amount of light coming in, and the rhodopsin on the retina is bleached to reduce sensitivity. But under very dark conditions, the iris is fully open to capture as many photons as possible. And as the rhodopsin is slowly replenished, the photoreceptors themselves become much more sensitive. And that is why it takes time to dark adapt. And only a brief exposure to bright light will stop down your iris, bleach the rhodopsin, and dampen down the system. And that's why it takes time to dark adapt. Now, excuse me, having a delicate photoreceptors buried below the nerves and blood vessels, right, makes it easier for the body to maintain and protect them, but it's a distinct disadvantage that in order to reach the brain, the optic nerves have to tunnel through and the wall of the eye in order to reach the brain. And at this area, which is called the blind spot, there are no photoreceptors. So the eye has no capability to see anything that is imaged on that part. However, because of the asymmetrical state of the eye, as you can see here, higher sensitivity and highly acute portion of the vision is here, and the corresponding opposite side with the other eye means that the brain will fill in information in the one eye in its blind spot with the information received from the other eye. So we generally don't realize that we've got a blind spot. However, in astronomy, we only use one eye at a time, typically. And so the blind spot can become more apparent, and the view through an eyepiece is, in fact, an unnatural thing. So if you have a bino view on your telescope and you're using both eyes, then you can take advantage of the brain correlating information from one eye versus the other in order to fill in the detail. I hope I didn't overload you with that. So just a little sort of summary here. What we've got is a graph showing in the green the cones, and in this purple the rods, right? And in the center here is the fovea, right? This side to the right is towards your nose, and this side to the left is towards your ear. You'll see that there's an asymmetrical distribution of sensors, and that the cone density is very much higher right in the fovea there. And the numbers are staggering, really. The fovea centralis, or foveola, is only 0.3 millimeters in diameter. There are no rods there, and the structure is optimized to prevent light scattering. There are no blood vessels to obscure it in that area. And so this is highly optimized for acutely high resolution imaging. Now the eye also dithers, which means that it's continuously moving, it's vibrating left, right, up, down, just small movements to keep the light from the object of interest falling on the fovea centralis, right, where the bulk of the cones reside. Astronomers use averted vision. This is something that takes concentration, and what you're doing is you're positioning the image just off center, not there where in normal life you will want to aim your eyes directly at the object of interest, right? We use averted image to put it just a little bit off center. And the result of that is that we can use the more light sensitive rods, right, which as you can see rapidly increase in numbers just outside the fovea here, right? And rods are 1,000 times more sensitive than the cones. That's quite a difference in sensitivity. Unfortunately, despite the rod's sensitivity to blue, detail in blue is difficult to see. And that's because we saw the blue cones lie a little bit outside the fovea. And the eye is naturally focused for red-green. And so blue tends to be a bit out of focus. So getting high definition blue is not really possible. Now, a little aside here, incidentally, the additional glia in the retina, these are other ganglion cells that are blue sensitive, but they do not contribute to vision. And their purpose is to prime the body's diurnal response to ambient light, and influences, consequently, the balance between insulin and glucose. And as a result, blue artificial light can have profound health effects. So, basic specification of the eye. We're almost finished with this section. Our total field of view, about 100 degrees, field of fair definition, 48 degrees, field of good definition, in the macula, where we have both the blue and the red and green cones, about 10 degrees, and the highest definition is only a half a degree, right? That's a very, very small area. So we rapidly lose the detail as we move from the center of the eye towards the edges, right? Yet the maximum angular resolution is 1 to 2 arc minutes, right? And the dynamic range is greater than 1,000 between the faintest object we can perceive and the brightest, right? That's quite staggering. Quantum efficiency is quite good. And as a matter of fact, some of the cells can even detect single photon events. Now, the half a degree field of highest resolution just happens to be about the same size as your little fingernail if you hold your hand out at arm's length. And notably, this is also the angular diameter of the moon. My question is this a coincidence, right? So, because the resolution drops off towards the edges, right, the outer edges are really only good for detecting movement. And for this reason, you'll see that eyepieces delivering over about 40 degrees apparent field of view are actually luxuries, right? Nice to have, but 40 degrees is quite a reasonable maximum. Quantum efficiency is boosted with the rhodopsin, and the neural processing plays a big part in sorting the signal from the noise. So I find this fascinating, and I hope it's been of interest to you. Now I want to do a little experiment. This looks like a rubbish slide to you. I mean, I bet you can't read this. Well, of course you can, right? Well, I would like you to just pay attention to this. Just look at this part. Now, although this was designed as an experiment in an auditorium for like projection, the normal sort of distance that your screen will be makes this quite reasonable. Now, I ask you, if you're looking at the little red dot there, can you actually read the rest? You can answer me afterwards during the Q&A, because I would really be interested. Just give you a second to focus there. Okay. So even though you already knew what the text said, you probably couldn't read it. Now, the good news here is that the worst part of the image is almost invariably at the edge of the field of view, where the eye is also least discerning. And for most purposes, the aberrations are small enough to be tolerable, if not imperceptible, outside of your critically focused part of the eye. So again, this shows that you really can get by with less expensive eyepieces having narrower fields of view. Now, I'm not going to dissuade you from spending the money and enjoying the modern technology. I just want you to be aware of what's really going on and choose wisely with your eyepieces regarding your preferred targets. Now, seeing objects that are faint and discerning detail. With your knowledge of the eye, you'll understand the critical factors, dark adaptation, but also the image surface brightness. So here on the right, we've got the same thing that gets magnified. And as we magnify it, we're taking that same number of photons that's inherent in the image, and we are spreading it over a larger apparent field of view. So it goes from being brighter to fainter as we magnify the image, because we're spreading the same amount of photons over a larger area. But to a degree, fainter detail can be seen, right? But after a while, you get to the point where the image is breaking down, right? Now, on the fringes of visibility, the brain correlates the information from the adjacent ganglia and votes on whether or not there's something actually there. So that is something to consider. If you look around a little bit in your eyepiece, you might actually see more detail because the eye is giving the brain information to vote on. I must note that foreground stars are point sources, sorry. So they will look the same irrespective of the magnification. As you magnify up to the point that they break down into blobs because the instrument's levels of definition are reached, it will just be a point. Now, unless you've got severe astigmatism, it is better to observe without the glasses. But if you have astigmatism, then the points are going to turn into little spiky things, which is where this whole star should we say, comic cartoon, the illustration comes from, the little spikes. They aren't there, but that's because some people have very bad vision. Now, counterintuitively, it can sometimes be better to pile on just a little bit more magnification, right? And that will reduce the exit pupil, and I'll go into a little bit more detail later. By reducing the exit pupil, it means that you're not using the outer parts of your cornea where the quality of the eye is not so good, right? So use less of the eye's lens, but by spreading the image out, you'll be using more ganglia, right? So now this is a justification for the experienced observer to have a greater selection of eyepieces suited to the objects of interest, because that way you can optimally match the image to the nature of your eye-brain system to be able to see just that little bit more detail. So in summary, our visual acuity drops off rapidly. So I ask if 40 degrees field is adequate, then why the move to extreme wide angle? And I mean, you have to roll your eye around to see the field. And again, the answer is that for large untracked telescopes, such as big Dobsonians, the wider fields allow the object to remain in the field longer before having to push and then wait for the vibrations to die down. People do find them more comfortable. And in the end, it's like so many other things in life. You know, if you've got big TVs and performance cars, once you've had them, then it's hard to go back to something less. So let's just be grateful that we're no longer using the tiny Ramsden lenses and the 0.965-inch barrels. Okay. I would like to touch now on the subject of how you're going to be selecting eyepieces optimally. And the big word is magnification. I think this is very much over-considered, right? So what is magnification? It's a ratio of the telescope focal length, the eyepiece focal length. It's also a ratio of the apparent field of view to the actual field of view, and the entrance pupil, that's the diameter of your objective, to the exit pupil, which is the diameter of the little beam of light leaving the eyepiece. Now, these three formulae are all related, so you can equate any two of these as you like, and with simple algebra, work out some interesting things. So, firstly, what I want you to know is that an eyepiece of a given focal length will produce the same exit pupil size for all telescopes of a given focal ratio, right? So this helps us a lot to normalize the question of magnification across instruments by choosing to describe magnification in terms of the exit pupil size instead, right? So this then will enable us to assess the suitability according to an instrument's characteristic F ratio instead of the objective size or the focal length, right? And it also allows us to take the eye's characteristics into account intrinsically. So we've just seen that as you increase the entrance pupil, as your iris expands, you're using the outer part of the lens, which is less good quality, your eye's lens, right? So, as I said, stars are pinpoints at infinity, and their brightness in the eyepiece is therefore invariant of magnification. They remain pinpoints. The apparent brightness depends on the magnitude and the aperture of the telescope. Right? So their relative position in the apparent field of view will change, but the rest remains the same, irrespective of what eyepiece you put on the telescope. I mean, assuming quality. However, the extended objects do magnify, and the same amount of light is then spread over a larger field as you magnify. we've got to consider light pollution and sky glow, which are also extended objects. So if you increase the magnification slightly, you may be able to see fainter stars because the stars are pinpoints and their image is not being expanded, but the sky glow is a wide field thing and it will be reduced because it's spread over a larger area as you increase the magnification. And as a result, there will be more contrast between the stars and the sky glow. Right. Now, every telescope suffers from various aberrations, one being diffraction. Diffraction is worse in obstructed designs. That's things that have got something blocking the incoming beam, like Newtonians and Schmidt-Cassegrain telescopes, which have got secondaries hanging in the middle. And so most reflectors, in other words. But even unobstructed designs are influenced by diffraction, because you've got diffraction from the edges of the telescope's aperture. Now, excessive magnification also.
Sorry, Chris, can I just chip in quickly?
Yes.
Normally we go on for about an hour. You've been doing very well. Can you just give the listeners maybe a bit of an idea how much longer they will be watching? I mean, it's very fascinating. Interesting. You're giving us great value here, but
okay. So I'm probably like 3/4 of the way through.
All right. Yeah. So another 20 minutes or 30 minutes or so.
And I'll try and speed it up slightly, right? There's some others where I won't talk so much about it. You know, I had 1 or 2 slides where I had a lot to say about one slide, but the rest will go quicker, I think.
Okay, thanks.
Okay, right. So every telescope does suffer from diffraction, and it's worse in obstructed designs, but even unobstructed instruments do suffer from diffraction. And as you pile on the magnification, then it also magnifies the fuzziness that you get from the diffraction. So, you know, you can't escape the laws of physics. There's no such thing as a free lunch. And this is where the term empty magnification is important, right? This denotes that what you see when you magnify beyond the limits of resolution. So the image is bigger, but it's also fuzzier and fainter. You've run out of detail, and magnifying more is not going to be helpful, right? So for any instrument, there will be a limit to what you can sensibly use as the magnification, right? Now, I talked about the exit pupil. This is really, really important, right? So as we said before, the purpose of the eyepiece is to match the eye to the telescope, right? Now, exit pupil is the beam of light leaving the eyepiece, and in the daytime, it looks like a bright little disc that's sort of floating just outside the eye lens of the eyepiece. Most instruments have a central obstruction, and if we draw the exit pupil like this, the central obstruction produces basically a shadow or a hole in the center of the exit pupil, right? And at low magnifications, the exit pupil gets bigger, and this then means that you're not going to use the good part of the eye's lens, right? Because the exit pupil is going right out to the edge of the eye's pupil, and it's using the periphery of the lens, which is not good quality, right? And so this, of course, is worst with fast telescopes, because the fast telescopes intrinsically like to produce large exit pupils at low power, right? Now, every part of your cornea that the exit pupil passes through contributes to the image, and the optical quality of your eye is worst around the edges of the lens. So at low power, when there's a large exit pupil, then no eyepiece, no matter how perfect, can show truly pinpoint stars. And that's because you're using a bad part of your lens, right? Your cornea. So the eyepiece is fine, but your eye's lens isn't, right? So this shouldn't stop you. You must just be aware of it. Now, remember, I also spoke about the blood vessels on the surface of the retina. At high magnifications, you can have a very tiny little beam coming out, right? Very small exit pupil. And then these start to become similar to the size of some of the blood vessels and it throws shadows then onto the retina, right? And so that is not cool, right? So you just can't win. So I'm not saying that you shouldn't explore these extremes of ultra wide or ultra small exit pupil. I just want you to be aware of what the trade-offs are, right? Now, I promised you an anecdote earlier on the subject of exit pupils. So I've used a 0.63 times telecompressor on my 10-inch Schmidt-Cassegrain grain and put on a 75 millimeter eyepiece. And this achieved extremely low power. It gave a huge exit pupil, far bigger than the eye's pupil, right? However, by offsetting my eye so that the pupil was on the annulus of light coming out of the telescope, right? It was possible for me to use the system quite satisfactorily. Now, of course, the majority of the light coming out of the telescope was wasted because it couldn't get into my eye. However, it still gave the very brightest possible image at that magnification with the full resolution of the telescope. And this enabled quite detailed views of Barnard's loop, which had been quite an elusive object for me for many years. Because it's important to consider the exit pupil, we should actually know how our eye itself is behaving so that we can make sensible choices, right? So I encourage you to measure your pupil size. Now, how do you do this? Well, it's actually quite simple. You get an object of known diameter, and I would suggest a rod rather than some strange shape, and drill bits are good for this because you can get them in very, very specific sizes. And in the small sizes, at least in 0.5 millimeter increments, so that you can find smaller increments than that. And you hold this rod in front of your eye, right? And you look at a star. Now, the stars are very far away and they appear essentially as point sources, but in fact, the light from the star is coming in as essentially a parallel beam. So this beam is bigger than the size of the Earth, but all that matters is what's reaching our eye. Because it's coming in parallel, it means that on each side, it's going to skim past the obstruction. So you could use an Allen key, which has got 2 diameters because it's hexagonal in cross section. That gives you something you can measure with verniers and a known diameter. So you just move the object a little bit sideways, right? And if the target remains visible, then you know that your pupil is bigger than the diameter, right? On the other hand, if you move it a little bit and you can't see the star, then it means that the pupil's totally covered, right? And if it just blinks in and out, then you know that it's basically the same diameter as that object. So you'll find it quite instructive to try this under different conditions where your eye is better or less well dark adapted, and try and find out what your limits are. And this will help you to know whether buying that low power eyepiece is really sensible for your eyes, right? And the objects you like to observe, right? So it helps to know what your maximum pupil size is. Remember, small children can maybe dilate to about 5 millimeters, but as you get older, you can struggle to manage 5 millimeters at best. This is because the tissues lose their elasticity. Now, I'm often asked, what's your favorite focal length? And it's sort of meaningless, because it depends, right? What is it that you like looking at, right? Under what conditions, right? Which scope are we talking about? And are you dark adapted, So these questions can be quite tiresome, but I understand why people are asking them. It's because they want to know what they should buy, right? And for this, as a generality, right, generalization, you should say your favorite eyepiece would be one that's comfortable, sharp, and that produces a medium power. So that's something with an exit pupil around 3 millimeters in diameter and with a reasonable apparent field of view, right? And the appropriate focal length eyepiece to achieve that depends on the focal ratio of the scope, right? So if you read in the media, you'll have people talking about so much magnification per inch of aperture. I consider this to be nonsense. It's really counterproductive. Just concentrate on the required exit pupil size, and this will be the simplest and most appropriate method. Now, I have to point out that an eyepiece set that's chosen for a particular focal ratio of telescope will work for any telescope having a similar focal ratio, independent of aperture. So I've got a 4-inch, an 8-inch, a 12-inch, and a 14-inch Schmidt-Cassegrain. They're all f10, but they're very different instruments, but they're the same focal ratio, and the same range of eyepieces will work perfectly on all of them. So it's not a question of the size of the instrument, it's the focal ratio that counts when choosing your eyepiece focal lengths, right? Now you must remember that under light pollution, you don't fully dark adapt. So if you're mostly observing in the town, getting something with a very large exit pupil is not going to be helpful to you because your eye is not fully dark adapted, your pupil is not as wide open as it can possibly get. And so you're going to have much of the light not reaching your eye. It's going to use the outer portion of your cornea, which is not so good. And you will have that if you've got an obstructed instrument like a Newtonian, you've got that hole in the middle to deal with, right? So this is what I would suggest, right, in a good range of eyepieces. So your maximum power is where you get about a 0.5 millimeter. You will seldom use it. It'll test your instrument to the limits of its resolution, and it demands utterly stable atmosphere. If you go to smaller than this, now you're in this empty magnification thing where it's just useless, right? On the opposite extreme, right, if you are young and you've got dark sides, right, well, then you could go to a 6 or 7 millimeter. You're probably never going to actually achieve your 9 millimeter that a small kid would, right? Some people do. And if you know what your eye is capable of, having measured your pupil, then this will be useful, right? But generally, I would say 5 millimeter for us if we're older or if we're not enjoying very good dark sights, right? So that's the set. Now, I would say get your medium power first, then get your low power, then get a high power, and then you can start filling in if the targets of opportunity require more. I strongly suggest that less is more, right? Get the best you can afford, better a few eyepieces than some mediocre ones, right? Okay. Buy in that sequence that I said, first get a medium, then a low power, then a high power. And then finally, you can explore the extremes, and maybe a good quality Barlow will help you there. But remember that some eyepiece designs do include the built-in Barlow, and then they don't Barlow very well, right? The care and storage of your eyepieces is quite important. I mean, some of these eyepieces are tremendously expensive, right? And so you don't want something to happen to them. Every eyepiece deserves a case, right? This is what I put in my eyepiece case. It's a little sachet of silica gel, right? The point here is the eyepiece is outside, it's cold. You bring it inside where the air is warmer and it'll have more moisture that it's taken up. And now your cold eyepieces are good condensation sites for this. And then you close your case and you put it in a cupboard. And now what you've got is wet optics that are sitting there in the dark, right? And this can promote fungal growth. So if you have the situation where you must come in from the cold into a warm, moist environment, Rather put your eyepiece in a Ziploc bag, bring it in, let the condensation happen on the outside of the bag, and later when they've got to thermal stabilized thing, put them in your eyepiece case. Make sure that you've got a desiccant in there for storage, right? Good eyepieces will last for a lifetime, and so rather treat them as being of long-term importance, right? Even basic eyepieces really do deserve to have a case. You're less likely to lose them, they're less likely to get damaged. So, where to start in your set, right? What telescope have you got, right? Will you be going to something with a larger focuser, right? If it's possible, but it's not likely, then maybe you want one of these things with a combination barrel that can be 1/4 to 2 inch, right? Cost, well, as your apparent field of view goes up, so the cost goes up, and you're facing the law of diminishing returns. By all means, if you want to get your 110-degree thing, but like I said, you know, if it's in the 40 to 80 degrees, that'll be fine, right? Okay, remember that your scope might go out of balance, right? For ease of use, a set that is parfocal is quite convenient. So parfocal means that when you change eyepieces, you don't have to do much refocusing. And as a result, maybe you don't lose the object, particularly at high powers, right? But quality is king. You at least want an orthoscopic or a superplussal. But if you've got a short F-ratio telescope, you need more. Remember, there will always be advances in designs and materials, but the physics behind this all stays the same. So I say be practical, be careful what you wish for, because you might get it, and buyer's remorse is painful. Don't be in a hurry, be discerning in your choices, right? And for this, consider secondhand. There are bargains to be had. There's always somebody wanting to trade up, or people wishing to rectify their mistakes. So if you've got a short focus refractor, your needs are different from if you've got a long focus Schmidt-Cassegrain, right? There will be an overlap, but just be careful in your choice. Finally, you can do it yourself, you know, and I'm not joking. All of these are eyepieces that I built, right, out of junk. These the two bigger ones, are 8-element eyepieces, 50 millimeter field of view, right? This is a 1 1/4 inch, that's a 2-inch eyepiece. And I actually swapped one of these for this Teleview 3.7 millimeter ethos. That's a fantastically expensive lens. Now, how was it possible that I could swap this homemade thing made out of junk, right, for this exotic eyepiece? Well, the answer is that this lady bought this eyepiece and she put it on a Dobsonian, which immediately nosedived because of the weight. At 3.7 millimeters, she couldn't keep anything in the field of view. It just vibrated too much. A total miserable experience. Now, this is a wonderful eyepiece, but it was the wrong eyepiece for that scope. And so it was not being used. This, on the other hand, is lightweight, nice wide field of view, low power eyepiece, right? Exactly what she needed to fulfill her needs, right? So I challenge you, try making your own eyepieces. And if you want to know how, you can ask me. Now, just a few final words. We're talking about magnification here, right? Who's fooling who? All these gentlemen, right, in the days of visual scientific astronomy, they were highly respected, highly skilled observers. And they used extreme magnification to try and tease out detail in Mars. And these are the kind of maps that they drew, right? However, other people didn't see the same stuff. So the question is, what's going on here? Now, there was a theory, which I think has got a lot of merit, that at least for some of them, what they were seeing was the blood vessels in their eyes, right? Because of this tiny, tiny exit pupil caused by the extreme high magnification, and they were seeing structures within their eyes, right? As soon as the space probes became available, we see something very different. And I have to say that when I was sketching Mars at a close opposition, my sketch looked a lot more like this picture than it did of those, right? But there can be another solution to the question. A guy by the name of William Hartmann, who was a Mars imaging scientist from the 1960s to the 2000s, explained that the canals that were drawn here could actually have been streaks of dust caused by wind on the leeward side of mountains and craters that just sort of gave a contrast there that people could see. But I just want you to be aware that high magnification is not the be all and end all. And at that, I say thank you for your attention. I did say that I've got a couple more slides on filters if you would like to know about that, but that's deviating a little bit from the topic. So there we go. Over to you.
Thanks very much, Chris. That was brilliant and very comprehensive. I'm definitely going to watch this one a couple of times, the recording. And for those people that have missed the beginning of the talk or whatever, they just need to ask for the link to the video when I send it out. I feel after watching this talk that maybe I should go and get my optometrist certificate tomorrow. I think I can qualify, start an additional job. So yes, I've learned a huge amount about stuff that I never knew. There were questions answered that I didn't know existed. Okay, thanks very much for that, Chris. Anybody in the audience with questions, please go ahead and ask.
I'll stop sharing for the moment. If you want me to bring it up again, I will.
Okay. All right. I've just got a quick question. I don't know if this is too off topic. You know, we've got a few club telescopes and things, and one was given to me, a nice one, but I don't have the money to buy these fancy. I do a bit of astrophotography, but I use my, DSLR that I use for normal photography as well. And what is the optimum way of finding the optimum sort of distance for the best focus from the, when you take the eyepiece out, put the T-piece on, what is it, the best way to find the correct distance from the eyepiece sort of entry point?
Are you talking about for eyepiece projection?
Yeah, for projecting the, no lens in between directly onto the sensor of the camera.
Yeah.
So you want to get that sort of, so that you're not making the image bigger than the sensor or smaller.
Yeah, this is difficult to answer because the mechanical structure of the eyepieces can vary so dramatically, right?
So I haven't got an eyepiece. I'm just putting the camera on at prime focus.
Okay, so you're asking telescopes. All right, so normally a Newtonian telescope would be arranged so that when the focus is collapsed, it's like pushed in as far as it can go into the telescope, that the image plane will be about an inch or 25 millimeters above the outside of the focuser. Now, if you want to put a DSLR on the system, then you've got to put a little T-ring on, and then the distance from the T-ring to the focal plane is about 50 millimeters. So that means that you need at least another 25 millimeters of outfocus in your focuser. Now, most focusers will manage that. And if the telescope has been constructed according to this sort of norm, then it's okay, but many people will have difficulty. If you're using a Schmidt-Cassegrain telescope, normally the focusing is conducted by moving the primary mirror, which is actually changing the effective focal length of the system. And that can provide quite a wide range of outfocus for you. So if you can't achieve focus, it probably means you can't push your camera far enough in towards the telescope. And if you're using a Newtonian, the answer to that is to take a primary mirror and move it up the tube towards the secondary. And that pushes the focus out, and that will allow you to achieve focus. You may, of course, get vignetting as a result of that, because the scope mechanics were probably not arranged to do that.
Okay, but to check the sort of point, can one just stick one eye in the sort of train and move your head back and forth and find the approximate sort of distance that is actually in focus without an eyepiece?
Well, you can, but I think you would find that difficult. What I would suggest is during the day, you find a distant thing like a mountain or a silver or something, right? That's easily discernible. You aim the telescope at that with the eyepiece. You take the eyepiece out and you put a bit of waxed paper on the focuser, and then you can rack it in and out and see the image, and that should tell you where it is.
So the sharpest distance is the ideal.
Yeah,
that's where your sensor must actually be. So you must measure the distance of your sensor.
Yeah, but your sensor's embedded inside the camera, and so it's a mechanical separation between the outer edge of the focus and where the image plane is. And with a 35mm camera, it can be difficult to achieve that. But with cameras that are designed specifically for astrophotography, they usually take that into account, and it won't be.
Okay, thanks. Anybody else? Questions?
Yes, I see that Andy has his hand up and Etsu has his hand up.
Okay. Andy, can you go first?
Andy, I think you're on mute. No, we still can't hear you. Maybe you switched to the wrong microphone.
No, we can't hear any sound, Andy. Something's not right there. Sorry, can we go to Etsu then for the moment?
Okay, Etsu.
Okay, can you hear me?
Yes.
Okay. And an idea came up to my mind while I'm listening your useful talk. If we make a very, very small Cassegrain type telescope or Newtonian, it could be used for the eyepiece, but I haven't seen it before. That I thought the reason the eye point came up inside of the tube, and second, the image makes very bad because of the secondary mirror if the reflector used as an eyepiece. What do you think?
I'm struggling to visualize what you're saying. You're saying to use telescope as an eyepiece.
Yes, reflector, not a reflector, Newtonian or Cassegrain type reflector could be used for the eyepiece if we make it small, very small, 1 inch or 2 inch, and very short focal length. But I haven't seen it before.
Yeah, look, I think that's quite difficult, huh? Optimizing the image is more than just putting a simple lens in the train. So yeah, I'm not sure how to. It's a peculiar question. I'll have to give it some thought.
Yeah, the eye point could be not be out of the eyepiece if we make a Cassegrain type eyepiece or Newtonians. The eye point is inside, just in front of the primary mirror. So if we used the small CCD tip instead of the eye, it would be useful as an eyepiece. The reflectors could be used as eyepiece. But
well, that's interesting. I suggest you try it and you tell us what the results are.
Okay.
Sounds to me like an intriguing proposition. Maybe if you could put your idea on an email and send it to us, and just so we can get a better idea of what you're talking about. But I think what you're trying to say is the reflective like a reflective telescope, you have less aberration of the light than with lenses, like in a refractor. So it's less complex and less loss of definition and so on. So if you had an eyepiece based on that principle, it might be sort of more, give you a clearer image, is what you're saying.
Yes, thank you.
All right.
Good, Derek.
Can I try again? Can you hear me now?
Yeah, we can hear you now, Andy.
Yes, Andy. Welcome back.
Right. Thank you. I always seem to have problems. Anyway, Chris, what I wanted to ask, you did mention wearing glasses, you did brush on it, but I'd just like to know, under what circumstances should one wear glasses while looking through the eyepiece? Is it only if you've got astigmatism to correct for that, or in my case, I'm long-sighted and I take, I need quite strong reading glasses, about 3 diopters, but I prefer to look through the eyepiece without glasses, but then it's a problem looking at star charts and that, then you have to put your glasses on. So my question is, under what circumstances should one use one's glasses?
Well, if you suffer from short or long distance vision, so presbyopia or myopia, then the easiest is just to refocus the telescope and it'll take care of that, no problem, right? So really it is astigmatism that is the main problem. If you've got things like macular degeneration, then nothing's going to help, I'm afraid. But in terms of optical defects in the eye's lens, right, astigmatism is the worst case, and you can certainly wear your glasses for that. And in that case, the eye relief is quite important so that you can still get the exit pupil to meet your eye's pupil for optimum coupling between the telescope and the eyepiece.
Yeah, okay, thank you.
If you don't have that amount of eye relief, then you can still use your glasses, but you're not going to see the full field of view, and it'll be a little less satisfactory.
Yeah. Okay, thank you.
Okay. Derek, can I share some of my ideas that I picked up from Chris's talk?
Yeah, please do.
2 things. Like, one was averted vision. It always bothered me, like, what's the proper way to do averted vision? So I did some studies or some research on this thing. The blind spot on your retina sits on the side of your eye away from your nose and slightly below the center line of your eye. So if you want to use averted vision properly and you use your right eye, you keep the object of interest in the center of the field, and you concentrate your vision just to the right and slightly up. In other words, away from your nose and slightly up from the center. That puts the object on the most sensitive part of your eye.
If you are right-eyed.
If you're right-eyed, if you're left-eyed, you look to the left and up. If you do it the other way, you can by accident put that object exactly on the blind spot. It's actually, when you're bored at night, it's something that you can try and see if you can unsee the center of your field. And the other thing, Chris, with the exit pupil, I've actually made a spreadsheet, and if anybody, if I may share the spreadsheet, and then if anybody wants to use the spreadsheet to choose eyepieces, I think this will clear up this exit-pupil business quite well. So if you don't mind, if I can share that screen of mine,
Yes, please.
I will quickly.
Go ahead, share. Yeah.
Share
Multiple
this.
sharing is enabled.
Okay. You can see the spreadsheet. What does have? You can choose your diameter of your objective. I've taken 150, which is 6-inch. Your F ratio of the telescope, whether you have a Barlow lens or not, and choose the power of your Barlow lens if you decide to choose. What this then does, it tells you what is the effective focal length of your telescope, 1200 millimeters, and then a range of exit pupils that different magnifications will produce. And then in order to get that exit pupil, it recommends a list of eyepieces. Now, on some telescopes, the eyepieces will be a ridiculous eyepiece. But for best resolution, for instance, it will be at 100 times magnification and exit pupil of 1.5, and that's a 12 millimeter eyepiece for this one. Your sweet spot of a telescope, and that's something that I also found by accident, is that the magnification that is half your diameter of your objective is generally the sweet spot of the telescope. In this case, it's a 16 millimeter eyepiece. And now if you choose the same F ratio, but 10-inch, lo and behold, exactly the same set of eyepieces, because it is, as Chris said, dependent on the F ratio. If you now change that to an F5, your set of eyepieces to achieve the desired exit pupils, and your between 1 and 3 range is going to be the optimum range for this telescope. And then some advice, and below 1 millimeter, your exit pupil just becomes uncomfortable, and below 0.5 millimeter. So if anybody is interested in acquiring this spreadsheet, I will send me a mail and I will gladly distribute it. So I will stop sharing now.
Thanks. That looks very useful. I definitely want a copy of that.
Yes. Chris will definitely have my email address if you don't have it on your side.
Okay. Thanks very much. I'll look for it. If there are no other questions, I'd like to ask Chris if he can share us, if he's got maybe a couple of images of some of the projects, interesting projects he's done in the past in the way of telescope making. A bit of tonight's.
Sorry, Derek.
Yes, hello.
I don't have a question. It's Laura. I don't
Yes.
have a question, but I just want to say that the sound quality has been absolutely excellent this evening. The best so far.
Okay, thanks. Okay, nobody
Thank
else
you.
got questions
Thank
on
you.
the eyepieces for the moment? If are there any more? Okay, Chris, can you share some of your lifetime achievements with us? In other words,
This is a bit difficult, you know. A lot of the things that I've made, I've given away. This is what happens in the world of amateur telescope making, you know.
Mm.
Let me think if I can find something here.
What about the angel scope?
Yeah. Let's have a look. Finding pictures is not as easy as it sounds. But I had stuff, in my my collection of photos that I carefully edited, and in a moment of irrationality, I did something that actually destroyed a whole pile of them that I'm going to have to get back again. It might be on a backup disk somewhere. Let's see here.
Chris, can I ask a question on your homemade eyepieces while you're looking?
Yeah.
The design, the lens design in your eyepieces that you make, and do you make the lens 100%, or you do get old binoculars with particular lenses and then adapt them, or what do you do?
Okay, what I've done is I've used, let's call it in inverted commas, found optics. So all kinds of weird refractive optics that have fallen into my hands, I've experimented with. And I've used portions of camera lenses, portions of binocular lenses, right? There are many instruments out there that have eyepieces that if you extract it from its system, you can adapt into a standard barrel so that you can put it into a normal astronomical telescope, and a lot of them can work quite well. So if you've got broken binoculars, then you've probably got at least one of the two eyepieces still functional, and you can remove that. It'll be of a size that's a bit peculiar, but generally it's smaller than a standard 1 1/4 inch eyepiece. So just making a little bush will allow you to use it. And binocular eyepieces tend to be quite good quality, right? Rifle scopes are wonderful because they've got very good eye relief and quite a comfortable apparent field of view. And a lot of them get broken in the felt, they get dropped on rocks or something, and people just throw them away because in this country to get them repaired is basically impossible. The vendors of such things don't have enough volume in this country to have a proper repair center, and it doesn't pay to send it overseas to be fixed, especially if it's mechanical, damage. So you can often find broken instruments like that around. But I have gone beyond that to use the objective lenses of binoculars in combinations to make up very acceptable wide field eyepieces. When I say wide field, it's not super wide field, but it's better than the 40-degree apparent field of view, which is already quite comfortable and suitable for most purposes. So you can easily get up to 50 or even 60-degree fields of view if you just play well enough. It's a little bit hit and miss, experimentation is required, but it's quite doable.
Okay, have you found anything you can show us?
I'm finding folders that are empty because something went wrong. As I said, I managed to destroy my photographic collection. Got here. Okay, I'm going to just search for something specific here.
If we've got questions on making telescope and so on, can we contact you, email you and so on?
Yeah.
Looking for tips and so on. I've got a half-built one in the garage, which somebody else started, and I'm scared to carry on with almost, you could say. I've got the Texero book and I've got all the things, but you're scared of messing things up sometimes.
Yeah, it's not good. Yeah. I've made lots of parts of telescopes and a few complete telescopes and some adapted telescopes where I've found something and I've just modified it heavily,
Yeah.
And of course I've helped a lot of people to build their telescopes. I'm finding this very difficult to
Okay, I'll tell you what, if it's a bit of a problem, we are running quite a bit late, and I think most people need to go. Thanks for the email address, Johan. So I think maybe we should wrap it up and put that for maybe a different talk for a different day on telescope manufacturing. Making it is quite a narrow field of interest, so it wouldn't be a huge audience probably. I mean, a lot of people are interested in it, but a lot of people don't get down to doing it properly.
Yeah.
Yes.
One more comment, Derek.
Yes.
I'm sure Mrs. Stewart is waiting very patiently to feed her husband.
Okay.
I said not to worry about it. Yeah. As a matter of interest, how long did that talk actually take? Because I did practice a bit, but
We've been going since 6:30, so it's actually about 2 hours. Yes, it's about double our normal time. So we had effectively a double session this evening for the price of one.
Okay.
But I've got a Zoom subscription, so the time limit isn't the problem.
Yeah. So sorry for those who got bored.
No. I think people had other commitments. They didn't expect to commit so much time, perhaps. Okay. All right, Chris, I'd just like to say thanks very much for a very, very interesting and comprehensive talk. And as I said, it is all recorded, so if people have missed all or part of it, they can contact me and ask for the link. Or if you don't mind, I'll just put it on a public link, and so if people can even search for it, they might find it. But otherwise, just ask me for it. Okay, so thanks very much, and let's talk again. And we must get you down to Hermanus sometime, as Pierre said.
Yeah.
It's much more interesting to get you here, physically look at things and so on. All right. So I'm gonna say let's wrap it up then for the moment, and perhaps in an email, if we can arrange for some future talk and talk about some of the stuff you've made and so on. All right. Thanks very much. And anybody else with any other comments or questions before we go?
Thanks very much, Chris, and thank you, Derek. Good night to everybody.
Thank you, everybody. I'll be leaving now.
Good evening, Hermanus. It was nice visiting you for the change.
It's a pleasure, and thanks very much for your attendance and all the interest.
Thank you. Thank you, Chris.
Okay.
Thank you, everyone.
It's all the
you.
best. Chris, thank you very much.
Thank you, Han.
See you Saturday.
Thank you, Chris, again.
Okay.
It's ask, where are you? Are you gone? You still there? Where are you?
Matt.
It's
You had an international meeting. That's from Japan.
Are you
Yeah.
in Japan? So what's your time zone there? You must have a very different time to us.
Almost 4 o'clock
Obviously
in the morning.
Wow, you're dedicated man.
I hope it was worth getting up for or staying late for.
Okay.
All right.
I had a nap yesterday night, night time.
All right. Thanks for joining us. And thanks for the interesting question on the eyepiece possible construction. I was very intrigued by that.
Thank you.
Okay.
Thank you.
Thanks
Bye.
very much for a
Bye.
great
Thank you.
effort, Chris.
Okay, you're welcome.
Okay. Cheers, everybody.
Cheers,
And by the way, maybe I should have a
Cheers, Jill.
maybe I should have a hand clapping soundtrack in future. I think that's one of the things we miss in the physical meeting. and handing over a bottle of wine. That's also missing.
Well, that would work.
All right. Thanks very much. And I'll say good night and I'll log off. I'll stop recording now and I'll log off. Thank you.
Okay.
Cheers.